is a constructor, which is directly followed by the corecursive occurrence of the thing that we are defining. Let's look at another one. What is the second element of S in this case? Well, it's the head of the tail of S, which is the second element of S, so we have no idea what it is. The thing is not productive, and the problem is somehow the tail function that occurs in between of the guarding constructor and the corecursive occurrence. Another example, this one is also productive, but it's not primitively corecursive anymore, so actually we have the right-hand side starts with the constructor, but what follows is not directly a corecursive occurrence, but another constructor. So I call this corecursion up to constructors. This one is a function that takes an infinite list as an argument, produces another infinite list. So EO stands for something like every other. This function keeps every second element in the list. And we assume that the input list, we can evaluate it at any point. And the question is, can we evaluate the result? Then yes, it's primitive corecursion constructor followed by the corecursive occurrence. So this one is more interesting. Here we use the function that we just defined. So okay, what is this first element of the thing? It's 0. The second element is 1. What is its third element? It's the first element of this. So it's 0 again. What is its fourth element? It's the second element of this, so it's the third element of S, it's 0 again. What is its fifth element? We have no idea. So there is something evil about EO in the same way there is something evil about tail. This one is easy. It's the pointwise sum of two streams, and it's primitively corecursive. I just need it for further examples. Nothing new. This is the shuffled product of two streams. So here something interesting happens. This looks a little bit like the product rule for derivatives in calculus. So you have two corecursive calls, and they are combined using a plus. So this is also productive. It's corecursive up to this plus operator. Because the plus operator occurs before the corecursive calls. Okay, another example. This looks familiar. This is obviously Fibonacci. And so the interesting thing is that this plus somehow occurs before the guarding constructors. And for each corecursive occurrence, you have one such guarding constructor in front of it, but on top of it, there is a plus. Yeah, it's obviously also productive. Okay, last one example. This one is a little bit weird. So before, all our corecursive calls were guarded by a constructor. So here we have this corecursive occurrence, it's guarded. This one, it's guarded. This one is not guarded. So is the whole thing then non-productive? Opinions? So it's productive. The thing is that if you look at the arguments to the corecursive calls, so in the unguarded case, the argument decreases. So in principle, we could unfold this definition n times and obtain only guarded corecursive calls. So this is what I called mixing recursion. So this is this unfolding, finite unfolding with corecursion up to plus. So everything happens somehow underneath of this plus. So those were my introductory examples. I think we've seen enough. So in the paper, we present a framework for defining all what you have seen and more. So and more refers here not to the unproductive definitions, but rather to codata types other than infinite lists. So we do all of it in a proof assistant. So our language is not Haskell, but Isabelle Hall. And to be clear, in proof assistant, an unproductive definition immediately leads to an inconsistency. So it's absolutely deadly. We don't need to prove that something is productive. I'll elaborate on LCF later. So in our framework, the user inputs the equations that we have seen, and sometimes the system asks him to prove parametricity or termination for some cases. Well, you might think, well, we take one undecidable problem, productivity, and reduce it to two, parametricity and termination. So the good news is that Isabelle has a very good automation for deciding both, not deciding, for dealing with both problems, parametricity and termination. And actually, for the examples I showed you, the user would not need to write a single line of proof. So this would be fully automatic. So let me give you some context. So what is the LCF philosophy? This goes back to Robin Milner. And the idea is not to trust anything beyond the kernel of the system you are working with. So, and LCF provers like Isabelle are safeguarded against unproductive or non-terminating definitions by not having recursion at all in the kernel. So, in general, the kernel of Isabelle is a rather boring type system and a rather weak logic and no recursion. It's still interesting that you can do interesting stuff with Isabelle, like verifying operating systems or Java memory models. So for 4 years now, we are extending, we are trying to make Isabelle a Corecursion-friendly environment. So we are educating Isabelle Corecursion, and we do all of it without extending the kernel, and this is the main challenge somehow. This brings me to related work. There is really a lot. So here I want to focus on the practical sides, in particular on proof assistance. So preceding this work, Isabelle supported primitive corecursion. It was implemented using a dedicated combinator for each coinductive data type. And I will show you in a second how this works. Cox Corecursion is slightly more flexible. It allows for corecursion up to constructors, and it's built into the logic. There are some problems with it. So people refer to it as broken because it breaks subject reduction. So the solution to this were co-patterns that were introduced in Agda recently. And they retain subject reduction, and in conjunction with size types, which essentially allow you to write productivity proofs directly in your program. This is probably the most advanced system for doing guarded co-programming. So size types are often perceived as a little bit too heavy, and basically you need to write the termination or productivity proofs yourself. In the program. So more lightweight extensions of type systems have been proposed, and I list them here. So in this work, we extend Isabelle's capabilities to support Corecursion up to so-called friendly operations. What we use for it is what we call a smart Corecursor, and in the rest of the talk I will be explaining the two notions. For the mixture with recursion, I refer to the paper. So let's get a little bit technical. So we start at what we have with Isabelle before this work. So this is primitive Corecursion. So this is the definition of infinite streams, much like Haskell lazy lists, but without the nil case, and I made this monomorphic for simplicity. So those are just streams of integers. So internally, this is viewed as taking some greatest fixed point of some functor. So there is a lot of ML code behind it. This is outside of the logic of Isabelle. This is but of course it goes through the kernel, so we can still trust this construction. And one of the artifacts that this thing generates is the primitive Corecursor. So it's a function of that type that comes with a characteristic property. So this is the hard stuff. Now we can just take a recursive definition as we had before of pointwise sum of two streams and massage it a little bit, plug it into the Corecursor, and we obtain a non-recursive definition of the O plus of this pointwise sum. So note that when we go from here to here, the constructor somehow disappears. So this is captured by this in times A. This represents the constructor, and the Corecursive call also disappears. So it's completely hidden inside of the A. This is somehow the state on which we do the Corecursion. And of course, we perform this definition, and the original specification is proved as a theorem by the Isabelle command. So yeah, while I showed you only streams here, this works, of course, in general for an arbitrary functor f, provided that it's in some sense well behaved. I don't tell you what a bounded natural functor is, but this is the notion which we introduced 5 years ago, and which is quite central to all of this work. So we have now this primitive Corecursor. How can we make it smarter? How can we allow it to have to allow Corecursion up to interesting things? So somehow this type here says where the Corecursion may appear. So the f basically says that the right-hand side of my definition has to start with a constructor, and it has to be given the unmodified arguments. This is the A. So the idea is to liberate this restriction. Suppose we can come up with a combinator that allows something to occur before the guarding constructor and something to occur in between of the guarding constructor and the Corecursive occurrence. So those are actually two black boxes which I highlighted differently. So this is the same thing that is allowed here and here. And it turns out we can come up with such a combinator to allow arbitrary many constructors on both sides. So we can, this box may represent arbitrarily many constructors. So in a sense, we have now Corecursion up to constructors, which is equally expressive to what Coq has. But now we can go further. So if we think of C as being streams again, we can somehow extend this smart Corecursor by allowing not only constructors, but also the pointwise sum operation. So somehow we extend this box and allow the user to use sums. So I show you the example of shuffle product. So how can we define shuffle products using this Corecursor? Well, it's almost as it was before with the primitive Corecursor. So we take the Corecursor specification, we massage it a little bit. So again, the guarding constructor disappears as we had before. The Corecursive calls also disappear, and the O plus is replaced by something that is much like O plus, but it's somehow lifted to this box. So it's a syntactic representation of the plus operation in some sense. And there are some etas, so this is just a return of a monad. So I tell you the box, the outermost layer of the box is a free monad or some functor. And then this definition is non-recursive. We can again prove the original specification as a theorem from this definition. And then, after we've done all that, we can further integrate the product into our Corecursor, so we can further strengthen the Corecursor. And now the next definition might not only use the plus somewhere here, but also the product in between. So we cannot do this for an arbitrary operation. We've seen that EO and tail are maybe not friendly, but the product is friendly, and the idea is that a friendly function should not peek too deeply into its arguments. Tail and every other function EO do peek too deeply. They are not friendly. So to capture the notion of friendliness formally, this is what we do. And I don't give you the full definition, but in some sense, the operation that is supposed to be friendly must be decomposable into some parametric component of a horrible type, and which is applied into within some fixed skeleton. So this is the actual raw, and so what we see here, it has access to the original arguments, S and T of the product. It has access to the head, the tail, the tail of the original arguments, but instead of streams, it has an A here. So this is why it cannot peek deeper beyond the first tail. So and the parametricity of raw ensures that it really cannot peek deeper. So this is what the user might need to prove parametric, but this is so simple that the system can do it. So in the paper, you can find more abstract, formal, and diagrammatic explanations of all this. Even more pictures that explain mixed Corecursion, some vaporware tool description. Well, actually, in the meantime, the tool is not that vaporware anymore due to an excellent intern, Aymeric Bouzy. And so the tool is 97% finished, and for example, it can already today define all the examples I showed you. So yeah, that was it. I conclude with a summary of the expressiveness of the most popular systems with respect to productivity. Thanks.
We have time for a couple of questions. Can you go back to your example of mixed recursion, co-recursion?
Yeah.
So is this something specific that you just don't tell us what it is, or is that just some completely made-up example?
Yeah, I had it on my last slide, actually. So S of 1 is an interesting stream. S of 1 defines the Catalan numbers. It's not easy to see, so it's somehow the Catalan numbers have to do something with the binomial coefficients, and this somehow builds the triangle. So the sum is basically the Pascal triangle somehow.
Okay. And how often does that come up that you need to have this mixed recursion, co-recursion? Because that seems to be one of your main selling points, that you can mix the two.
Yeah, that's indeed one of the main selling points. And for example, one can define functions as filter on streams using that. So it's a useful tool.
Yeah, I can confirm, probably less than a month ago, I was building semantics for a probabilistic language as potentially infinite trees, and we were wondering, is this thing really guarded, because we were using exactly this, and then we came across this paper, and then we were like, okay, we're fine.
But you have not tried Isabel to do this. No.
So back in 2010, Niels Anders Danielsen had a paper on beating the productivity checker using embedded languages. I don't know if you're aware of that, or like your friendly function seemed to so he turns that into a data type as an embedded language and somehow uses that to I can't remember the details, but someone used that to show productivity. Is that how does it relate to your work?
So I'm not 100% familiar with the work you refer to, but it sounds familiar. There are also category theoretic papers that do a similar construction. So the main contribution is expressing this within the logic without extending the logic within high order logic.
Thank you.
Okay, let's thank Dimitri again.